All right, guys, welcome to our second FRQ for the day. This one says that we are to sketch a slope field using our differential equation up here on the 9 dots that they've given us. So the first thing you want to do is pick a point that you want to actually find a slope at. So let's go ahead and do the one I just circled there. The coordinates of that point would be -1, 1. So if I were to plug that in up here, that would give me the slope. So we have a -1 for the x value and a 1 for the y value. And that's going to simplify to be -1. So the slope at this point is -1. Now negative slopes go in a downward direction. Okay, a slope of 1 is about 45 degrees. Okay, now if we pick this point over here, then the coordinates of that point will be 1, 1. Right? So we're going to plug that in up here to our little formula. 1 for x and 1 for y. That's a positive 1. And so for that one, we're going to have a 45-degree angle, but going in the opposite direction because it's a positive slope. So positive slopes go in this direction. Now anything on the y-axis or x-axis is going to be 0 because whenever those are 0, if you multiply 0 times anything, you get 0. So those are all going to be flat slopes. Down here, I'm going to go ahead and skip the work, but it should look something like this. Okay, so that would be your ending result if you were to sketch all of your slopes. Okay, but the same idea applies for the rest of these. Just plug some numbers in and get the slopes and sketch them. All right, guys, for part B, they want us to find the second derivative. Now, they've already given me the first derivative. This is the first derivative. So if I want to find the second derivative, then I need to take the derivative of that. And that's going to require the product rule. So I'll call that A and that B. So we do the derivative of A, which is 1, times B, plus A, times the derivative of B, which is 3y squared. Now, you have to remember we're doing implicit differentiation here, so we do get a y prime. Now, this is something that's not so obvious, but you got to remember this whenever it comes to doing second derivatives with implicit functions. When you do a second derivative with an implicit, this is supposed to be 2. When you do a second derivative with an implicit function, you're going to get a y prime, and what you're going to do is you're going to go back to what the original derivative was, and that's what you're going to plug in right there. And so we have y cubed plus x times 3y squared times the first derivative, which is xy cubed. And if we simplify this by multiplication, we end up with 3x squared y to the 5th. And there's my second derivative. Okay, so this first objective is done. Find the second derivative. Next it says determine the concavity of all solution curves in quadrant 4. Now quadrant 4 on an x and y axis is this quadrant down here. And in those quadrants, no matter what point you pick, the x is always positive and the y is always negative. So what we're going to do is the second derivative tells us about the concavity. So what I'm going to do is I'm going to plug in negatives, a negative for my y, and I'm going to plug in a positive for my x. Oops. And then we're going to simplify this. So a negative to the third power is going to give you a negative. And a negative to the 5th power is negative. If you multiply that by a positive, you get a negative. And a 3 is just going to still be negative there. So I have a negative and I'm adding a negative to it. The answer will be negative. So even though I don't have any numbers here, I can tell just based on the signs that the second derivative in this fourth quadrant here would have to come out to be negative. So we would say since the second derivative is less than 0 for all x greater than 0 and y less than 0. Now, what does that mean? Greater than 0 means we're on the right side, and less than 0 for the y means we're under the x-axis. So, or you could just say for all x and y in the fourth quadrant, that works also. So it says the second derivative is less than 0 for all of x greater than 0 and y less than 0. The function y must be concave down in the fourth quadrant. Okay, and there it is. Let's go ahead and move along to the next part. Okay, so then on part C, they want us to find a particular solution. So the first thing we're going to do is we're going to write our differential equation here. Next, we're going to separate our variables. So the first thing I'll do is I'll multiply both sides by a dx. Then I'll divide both sides by a y cubed. And now I've got my x's on one side and my y's on another. So now we're ready to integrate. So for the left side, I'm going to rewrite that as y to the negative 3. So let's go ahead and integrate now. If I add 1 to my power and then divide by that value, I get that. And if I add 1 to my power here and divide by that value, I get this, and we'll put plus c. I'm going to go ahead and rewrite that a little bit. On the left side, I'm going to put the y in the bottom because it has a negative exponent, and I'll just make the whole fraction negative instead of just the denominator. Okay, the next step is to plug in your initial condition. So I'm going to be plugging in negative 1 for y and 2 for x. So this thing over here simplifies to be negative 1/2. This one here simplifies to be 2. Go ahead and subtract 2 on both sides. And what would that be? I think it's going to be negative 5 over 2. Okay, now I didn't show my work for how I did the fraction work, but you do whatever you want with regard to fractions or decimals or whatever, but there's our c value. Okay, continuing on. So now I've got a particular solution. But now we want to get the y by itself. So the first thing I'm going to do is I'm going to get rid of this negative here in the front by multiplying everything by a negative. Now I'm going to take the reciprocal on both sides. Next, I'm going to divide both sides by 2. And then I'm going to take the square root on both sides. And we end up with y equals the square root of this big old nasty looking thing. Now we could have been simplifying then as we went, but this is an FRQ, and the more simplifying I do, the more likely I am to make an error, and so I'm going to say let's not. All right, now another thing we want to pay attention to is that whenever you solve one of these by taking a square root, you get a plus and a minus, right? And we have to decide, well, is our answer going to be a plus or a minus? Well, if you just look up here, the y value has to come out as negative, and the only way that's possible is if there's a negative on the outside here. So the solution is the one that includes the negative there. And that would be our final answer there. Okay. Let's proceed onward to the next one. All right, so for this one, they give us a slope field, and they want us to sketch some solution curves through the points that they've indicated there. So if I were to sketch a solution curve here, that's just going to be a straight line, because we just follow the direction of the slopes. At that point, they're all flat. Now, if I were to sketch a solution curve at the other point here, 0 and 5/2, I see as we go this way, it's going to go up, and then it's going to come back down again. And then for this one, it's going to go up and then come back up again. And then it looks like it might get flat here. I don't know. And then come back down. All right, guys, take a look at part B. All right, it says write an equation for the line tangent to the solution curve in part A at the point 0, 5, 2. So we need to find a tangent to this equation up here. So if we're doing the point 0, 5, 2, we need to get a tangent line. We need an x, we need a y, and we need an m. So we were at the point 0, 5, 2. So x is 0, y is 5/2. M can be found by plugging in those points into this differential equation here. Okay, so let's do that. I'll plug in 5/2 for for y. Plug in 0 for x. All right, so 5/2 is 2.5, minus 1 is 1.5. If you multiply that by 1, you just get 1.5 again. And then this is just going to be cosine of pi, because all the zeros go away. Cosine of pi is -1. Oh, sorry, this negative is not supposed to be there. And then you multiply, and then it becomes -1.5. So my slope is about -1.5. And therefore, the tangent line would be y equals -1.5 times x minus 0 plus 5/2. And there you have it. That's part B. Let's move along to our last one. Alrighty, so for the last one here, we want to be finding the particular solution. So I'm going to multiply both sides by dx first. Then I'm going to be dividing both sides by y minus 1. Okay. Next, we're going to go ahead and integrate both sides. Now, both of these are going to require some u substitution. Let's do the left side here first. Let's say u is equal to y minus 1. That means the derivative of u with respect to y is 1, which means that du equals dy, and therefore we have the integral of 1/u du, and the integral of 1/u is ln of u, and our u in this case is y minus 1. All right, so that side's done. Let's do this other side. On this other side, what do you think the u would be? The u is going to be this guy here. Pi is just a number, so it goes away. Now let's go ahead and substitute our stuff in there. We have x plus 1. We have cosine of u and du over 2x plus 2. Now this is an interesting little ninja move that we're going to do here that doesn't come up a whole lot, but it's possible. And so it's going to happen here. Watch this. On the bottom here, I can factor something out, can't I? I could take a 2 out, which means now these x plus 1's go away, and this 2 comes out to the front. And now we can integrate. So we have ln of y, ln of y minus 1 equals 1/2. The integral of cosine u is sine u plus c. And now we're going to go ahead and put the u back in. So for that side, the u was x squared plus, I forgot it. Let me look back up at it. 2x plus pi. All right. And of course, we don't want to forget our plus c here, which is our next step. The initial condition that they gave us was 0, 5/2. So we'll go ahead and plug that in here. So they're not very attractive numbers to work with. 5/2 is about 2.5. So I'll plug that in there for y. And plugging in 0 for x, all of that's going to go away and just leave me with pi. And sine of pi is 0, and 0 times 1/2 is 0. So this whole thing just goes away. And basically we end up with c is equal to ln of 1.5. So there's my c value. So we have ln of y minus 1 is equal to 1/2 sine of x squared plus 2x plus pi plus ln of 1.5. There we go. All right, the last step is to get that y by itself. So we're going to exponentiate both sides. We're going to make both sides become a power of e. On the left side, these go away. So I'm just left with y minus 1. And on the right side, we have an e with a big old exponent on it. All right. And then finally, we can just add 1 on both sides. So if I add 1 here, and we'll just put plus 1 over here, we can go ahead and just erase that, I think. And there it is. All right, and that's good enough for an FRQ. That's where I would stop if we had an FRQ, which it is an FRQ. But just to kind of point some stuff out to you, they could do this if you're like in a multiple choice test. They might expect you to do the following. So what you could do is anytime you have two things that are being added together in an exponent, you could split them up into two separate exponents that are being multiplied there. And then on this one, these cancel, and so you're just left with 1.5, which you could toss to the front here as a multiplier. Now once again, if this was an FRQ, I don't see any reason to do this. But on a multiple choice, that might be a helpful little move to know how to do. Okay? But there it is. So that'll end it for today. So hopefully that was helpful. We'll see you guys tomorrow.